This is Physics 2211 Lab 4. In this lab we are given video data, and we are going to use the tracker program and the VPython script to see if the energy principle is upheld. To do this, we're going to use Newton's second law and the energy principle. We are going to start with the tracker program. To do this, we're going to first place our axes with the origin at the attachment point of the spring and the negative y direction in the direction of the spring stretching. We are given a length scale, which is 0.7 meters, and that is from the attachment point to the center of the mass at the end of the spring. We can now harvest the point mass data from the different frames, and this gives us our graph to the right. From this data of time versus x and y position, we can gather the period data. The period is, of course, the time between the consecutive peaks and troughs. And over here we have gathered that data. Over here we have the periods from the x positions and the periods from the y positions. And we have graphs to visualize the data. The y positions are a little more bell curvy. Now the periods from the y positions are consistently less than the periods from the x positions. This is possibly because the path that the mass was traveling around is not circular, it is elliptical. And this means that the speed is not going to be the same around all parts of the ellipse, and this could very possibly affect the period in the y direction versus the period in the x direction, as we see here. We can then use this period data to find the spring stiffness and relaxed length of the spring, which are vital data. We know that the formula for period is that period is equal to 2 pi times the square root of m over k. Solving for k, the spring stiffness, we get k is equal to 4 pi squared times m over t. And if we solve this equation using the period data we just got, we get 6.83 as the spring stiffness. Using this, we can and the fact that in the initial frame of the video, the spring is in equilibrium, which means that there is no change in velocity, which means there's zero net force due to Newton's second law. We know that the spring force upwards is equal to the force of gravity downwards. So we can set mg equal to ks. Solving for L naught, we get L naught is equal to L minus mg over k. And if we solve this, we get L naught is equal to 0.123. These are the same values from the lecture videos because we are using the same spring and mass system. We can now use these data to initialize the VPython program. We have the mass as 0.402 kilograms. We have our initial position from the tracker program, the initial velocity, which is 0. We have our g, spring stiffness, relaxed length of the spring. We have the formulas for L, our unit vector, and S, the stretched length. We have the formulas for kinetic potential energies, which is the kinetic energy, which is 1/2 mv squared, potential energy, which is mgh, and the spring potential, which is 1/2 ks squared. We have our forces, and these forces add up to the net force. We have Newton's second law, which is V final equals V initial plus F net over m times delta t, and the position variant, which is position final equals position initial times V average times delta t. We have our spring formulas from earlier, and here we can calculate the changes in energy, which is of course the final kinetic energy minus the initial kinetic energy, and the final potential energies minus the initial potential energies. And then down here we have a line of code that allows us to graph these energies when we run the program. So here we can go ahead and see already that the energy principle is upheld. Now, because we chose our system to have everything inside it and nothing in the surroundings, we know that there are no energy transfers from the surroundings. We know that delta E total is going to be 0, and we can see that with this yellow line here being 0. As for the predictions versus the observations, we know that the red ball shows the observations from the tracker program. Those are just directly from the position data from the tracker program. And the blue ball is from the predictions of the VPython program. And we saw that as the program run, the blue ball followed the red ball very closely, and it possibly followed its path exactly. However, we did see that the blue ball was a little bit behind the red ball time-wise. Now, this does not mean it is a bad prediction, it just means that there is possibly an error in the coding somewhere regarding time. In conclusion, we see that we could use the energy principle and Newton's second law to find the energies of this system in this video, and we found out the energy principle is upheld and that energy is conserved. And thank you for watching.